It has to do with the expansion of the universe, and it's easy to explain using a baseball. Now, if I toss this ball up in the air, we all know what will happen. As it rises, it slows down because of gravity. Now, astronomers knew that the universe was expanding, and they assumed that the expansion would slow down because of the gravitational pull of stars and galaxies, just as the ball slows down because of the gravitational pull of the Earth. But when they actually did the measurements, they found something astonishing, something that rocked the foundations of physics. They found that the expansion is not slowing down, it's speeding up. It's as if I took this baseball, and when I throw it, instead of slowing down as it rushes away, it speeds up. Now, if you saw a ball do that, you'd assume there's some invisible force that's counteracting gravity, pushing on the ball, forcing it to speed away ever more quickly. Astronomers came to the same conclusion about the universe. That some kind of energy in space must be pushing all the galaxies apart, causing the expansion to speed up. Because we don't see this energy, the astronomers called it dark energy.
It's among the most important experimental discoveries ever in the history of science.
It took most of us completely by surprise.
And so we're still trying to come to grips with that.
Discovering that dark energy is pushing every galaxy in our universe away from every other at an accelerating rate was shocking enough. But even more surprising was the strength of that dark energy. For over a decade, scientists have been unable to explain why such a peculiar amount of it exists in empty space. Now, the idea that space contains any energy at all sounds strange. But our theory of small things like molecules and atoms, the theory called quantum mechanics, tells us that there's a lot of activity in the microscopic realm, activity that can contribute in energy to space. And according to the math, the amount of energy generated by that microscopic activity is enormous. The problem is, when astronomers measure the amount of energy that's actually out there, the amount of energy required to force the galaxies apart at the accelerating rate that's observed, they get a number like this. A decimal point followed by 122 zeros and then a 1. An incredibly tiny amount, very close to 0, and nothing at all like what the theory predicted. In fact, it's trillions and trillions and trillions and trillions of times smaller. Colossal mismatch.
We have tried everything to explain why the dark energy is as small as it is. We have tried everything, and everything fails.
Hopeless. I once called this the worst failure of an order of magnitude estimate in the history of science.
Does it bother us? Absolutely.
Finding that the amount of energy in space is so much less than our theory predicts is not just an academic problem. The precise strength of that repulsive gravity, well, that has profound implications for all of us. For example, if I were to increase the strength of the dark energy just a little bit by erasing 4 or 5 of these zeros, I still have a tiny number, but the universe would be radically different. That's because a slightly stronger dark energy would push everything apart so fast that stars, planets, and galaxies would never have formed. And that means we simply would not exist. And yet, here we are. So, why is the amount of dark energy so much less than our theory predicts, and also just right to allow the formation of galaxies, stars, planets, and life? We just don't know. The mismatch between the theoretical predictions of dark energy and what astronomers have observed is one of the great mysteries that science faces today.